Great. So what I want to do now is just give a quick summary of the finite element method, one element. So let's call it summary one element. So one element of what we've learned. Okay. So and then we're going to extend this towards the multiple elements. So first off, what we have is we had some structure. We maybe applied some prescribed displacements, we might applied some loading somewhere, and what we would then said was we had to mesh this, so we had to put nodes down, and if you do a single element, the whole structure is meshed by a single element, and that's associated with x1 for instance, x2 and x3. That's the way we typically numbered this, and then we said, okay, so this world we also map then towards this local world. We can map this to this this local world that we have. Okay. Oh yeah. See if this works. Does this right? Is that okay? Okay, there's something there. So this will also work. So essentially, yeah, that's better. So we could write this then as a psi equals to -1. Psi equals to 1, and then add these nodes here and 0 there. So that's essentially our psi world there. Okay, and maybe our x world started here. So that's essentially what we have. Okay, and from this, what we did was we could then set up a stiffness matrix with the associated unknowns, and then essentially we could have the right hand side of the forces as well. So associated with this, we had unknown Q1, Q2, and Q3. So associated unknown, this already is not great. It's visible, but it's not great. Unknown Q1, Q2, Q3, and then this was the node balance force balance at node 1, at node 2, and at node 3. Those were the forces that we had. These were the Q1, Q2, and Q3. So that's typically what we've done. Okay. So what we could do is we could map x and psi using isoperimetric formulation, set up all the information to set up our stiffness matrix, and this is typically called KQ equals to F. Okay, that's essentially where we were. Then once we've done this, we could then eliminate the displacements that were known, like Q1 for instance, and have the reduced system. We moved this Q1 multiplied by this across to the other side, solve for Q2 and Q3, and then in the end solve for the reactions at Q1. Okay, so let's just go again about what do we know and what can we summarize. So first off, again, the interpretation of the stiffness matrix is it's K equals to F. It's a force balance. Each equation is a force balance, and the force balance is at node 1, node 2, and at node 3. Okay, so this is essentially where we've put down our unknown nodes, variables. Those are also our places where we have those nodes are the nodal force balances. And in the end, we are solving this force balance to be exact. We're not making a mistake. This discrete system, the force balance that we do here for this discrete system, if I look at the sum of the forces here and the sum of the forces here and the sum of the forces here, in terms of this system, this algebraic system here, that I solve exact. And what we've seen is now from the finite element solution is the implication is that the more difficult problem, that continuous problem that we have, not just at these three variables, but at that whole field problem, when we plotted those solutions, we saw that those were only approximately in equilibrium. So what we've done is we've transformed a problem where it's very difficult to solve equilibrium to say let's transform it to a simpler problem, which is this algebraic problem with nodal Q's 1, 2, and 3. So set up a system of equations which we can solve for equilibrium. And we could solve equilibrium for the simple problem exactly, not approximately, exactly. Okay. The implication is that the more difficult problem is approximated as good as we can. That's really what this all boils down to. Okay. So this is the first thing that we just again said. The rows are associated with a KQ equals to F system. So this is force balance at node 1, force balance at node 2, and force balance at node 3. The columns are associated with unknowns, or not, with the displacements at Q1, Q2, and 3. Some of them are known and some are unknown. So column 1 is Q1, column 2 associated with Q2, and solid column this associated with column Q3, which is the mid-side node. Okay. If Q1 is known, then essentially we have to make sure that we isolate the unknowns, solve for them, and at the end, when we're done, we can then solve for the reactions, because when we have a prescribed displacement somewhere, so let's say Q1 is equal to 0, I know that there's going to be a reaction there that is not known. So once I've solved for all the displacements, these unknowns ones, then I have the whole displacement vector. I can multiply this with this to solve for R1, solve for our reaction 1. Okay, that is important to understand. So in this case, it would stuff it looks maybe something like this. Okay, so that's just again just to recap a little bit on that. The second aspect that I want to talk about is what are the properties of K again? We've seen now a couple of things about K. K is always symmetric. So K is symmetric. That's always the case, okay? That's non-negotiable. And that comes from the fact that we use the Bibnov-Galerkin approach. The weighting function and displacement functions are the same shape functions, the same form to describe those two systems. That's step one. What we saw is essentially the eigenvalues. The eigenvalues, so the K's eigenvalues, can be interpreted as is proportional to the strain energy. Okay, the eigenvectors are associated with the deformation modes. So the deformation that results in that strain energy. So this is what we were able to see with eigenvalues and eigenvectors. Okay, so that is important to understand there. The implication is, if eigenvalues are strain energy, what is my expectation? Is that the eigenvalues will always be what? It should always be. So if the eigenvalues, okay, eigenvalue is proportional to the strain energy, then essentially I expect this always to be big or equal to 0, because we saw the strain energy is 0 for rigid body modes. When we just translate the thing, then there's 0 strain energy, and as soon as we start putting deformation in, the strain energy should be something that's positive. So the eigenvalues should always be positive equal to 0. Another way of writing that is by saying, if I have an arbitrary vector x and I pre-multiplied with k, and I have an arbitrary vector pre and post multiplied with k, I want that always to be equal to 0 for x not 0. Okay, so for any x that I choose, I would like this to always be equal to 0, and this property is called positive definiteness, or positive semi-definiteness, because of the equal sign. So it's positive semi-definite. So this is another property of the K, which is just really interpreting this as a strain energy and saying, if that's the case, it must always be big. We can't have negative energy, otherwise we generate energy with the structure. And so the implication is that the K, this K matrix, is should always be a positive semi-definite matrix. This is just another way of saying this to make sure. That's part of the properties of what we have with K. Okay, and what we saw with K is there's always 0 strain energy modes associated with K. So we can't solve this full system. It's not solvable. This K is always singular. The determinant of it is 0. And it's because there's always a rigid body mode associated with what's going on. So at 1D, we have one rigid body mode. When we have 2D, we might expect to see maybe a rigid body mode translation, and maybe a rotation. We might expect to see 3. In 3D, we might expect to see 6, 3 translations and 3 rotations. But this is what we should expect to see, because in 1D, there's only one direction. So this is really just to quickly recap the summary of the one element, what we've seen, making sure that we just put a couple of things down, make sure we interpret this properly. Again, appreciate the fact that some of the nodes are known, some are unknown, that there are certain properties associated with the K that are interpretable. It's not just these things are eigenvalues and eigenvectors that we just compute. They have very specific meaning. Eigenvalues is related to the strain energy. The eigenvector is the deformation of that structure to give you that strain energy. And essentially, Some of them are non-zero, and if they're non-zero, they're always positive, and if they otherwise, they are at best zero. And that's a rigid body mode. So we can also then interpret all these things quite critically. Great, thank you.